This is video number 3 in our discussion of the synthesis of substituted arenes. We will continue working on these 3 learning goals, but now focused on the derivatization of nitrobenzene to aniline and aniline to aryl diazonium salts. Aryl diazonium salts, as you know, can be converted to many different functional groups. When you first learned electrophilic aromatic substitution reactions, you may have thought, wow, nitration seems boring. Although we've encountered the nitro group from time to time, we haven't really talked about what one can do with the nitro group or why it's a useful functional group in molecules. So I agree this may have seemed boring, unless of course instead of nitrating benzene, toluene was nitrated and nitrated to generate trinitrotoluene. Still boring? This is TNT. Okay, well, nitration is useful outside of the context of making explosives. So let's get serious and move on. We will start by proposing a route to procaine, which is an anesthetic agent, starting from benzene. So right now you will not be able to develop a complete synthetic route from benzene to procaine. But you should think backwards. You really should take a moment, pause, think backwards, and just at least draw as many synthetic intermediates in a retrosynthetic fashion that you can come up with. Just by identifying functional groups and thinking about both, obviously the acyl transfer reactions you know, as well as the electrophilic aromatic substitution reactions that you know. All right, get on it. Seriously, start your retrosynthesis. Identify functional groups and ask yourself, from what functional groups do I make this? 2 functional groups stand out here. 1, the aryl amine, and then 2, the ester. We have spent some time discussing how to make esters from benzoic acid and an alcohol. Acids and alcohols can be treated with catalytic acid to generate esters. Now, of course, there might be some complication because there is an amine and amines are basic, but we'll think about that later. Now, how to make aryl amines? Well, we don't know how to make aryl amines yet. So let's start learning how to do that. Aniline, which is an aryl amine, can be made from nitrobenzene by reduction of the nitro group with a metal reductant. Iron metal can be used or zinc in the presence of HCl. These conditions may remind you of the Clemmensen reduction, in which an aryl ketone was converted into an alkyl benzene following reduction of the carbonyl. Now, nitrogen certainly is being reduced here. It's making 3 bonds to oxygen in nitrobenzene and then 2 bonds to hydrogen, a less electronegative atom in the product. If you're wondering why there is a workup step, well, that is simply because reduction, and you do not need to know the mechanism, does lead to aniline or an aminobenzene. If this is substituted, it would be a substituted arylamine. Amines are basic, and this reaction is conducted in the presence of HCl, in the presence of an acid. Thus, once the aniline, the aminobenzene, is formed, a proton transfer reaction takes place to generate the conjugate acid of the aminobenzene. This certainly is the weaker acid when compared to HCl. It has a pKa of 5, whereas HCl is a pKa of -7. Thus, the salt is the final product of step 1, and step 2, a workup in aqueous base, just deprotonates the salt. This represents a neutralization. Add this process to your reaction chart, and let's use it in some problems. Propose a synthetic scheme for each of the following transformations. These products look relatively similar. There's an amino group and an alkyl group, specifically an isopropyl. However, in the first problem, there is a meta relationship between the 2 substituents. In the second problem, there is a para relationship between the 2 substituents. It is worth recalling that amino groups, aryl amines, come from nitro groups. Nitro is an electron withdrawing group and directs to the meta position. Isopropyl is alkyl is an electron donating group and directs to the ortho and para positions. Since there is a meta relationship between these two groups, we will use nitro to direct isopropyl to the meta position. So first, nitration to generate nitrobenzene. Then Friedel-Crafts alkylation. It is worth noting that nitrobenzenes are so electron poor because nitro is such a strong withdrawing group that Friedel-Crafts alkylations of nitrobenzenes can be difficult since the ring is required to act as a nucleophile in that reaction. It's required to react as an electron-rich species when it has this really extreme withdrawing group on it. So Friedel-Crafts alkylations of nitrobenzenes can be tough. Now, from this isopropyl nitrobenzene, you can reduce the nitro group with iron metal or zinc metal in the presence of hydrochloric acid. That will make the ammonium salt, and then this workup will deprotonate, resulting in the neutral amine. It is tempting for this second problem to be very excited and think that there are two ways to sequence the electrophilic aromatic substitutions in this problem. And that, of course, is because both the amino and the alkyl groups are electron donating groups. They're both ortho-para directors, and in the product, they have a para relationship. However, I have a little bit of bad news. Friedel-Crafts alkylation reactions are incompatible with amine groups, and that is because the nitrogen of the amine is a much better Lewis base than chlorine of the alkyl halide to generate the carbocation. So the amine will just coordinate to aluminum. So Friedel-Crafts alkylation of aminobenzenes is not possible. Now there is a solution to that, which is that you can generate the amide and try a Friedel-Crafts alkylation on that. However, that's really not necessary here because the other route, so alkylating first and then installing the amino group, will work just as fine since the alkyl group is an ortho-para director. So we're going to go with that. We're going to start with the Friedel-Crafts alkylation to generate the isopropyl benzene. Alkyl groups are ortho-para directors. Thus, the nitration reaction of isopropyl benzene will give the desired para relationship between nitrogen and the isopropyl group. From here, reduction with iron or zinc metals followed by neutralization under basic aqueous conditions give the desired amino product. Now that we've practiced using the nitration and reduction schemes to make aryl amines, let's try the procaine synthesis. We've identified that the ester functional group can be generated from coupling a carboxylic acid and an alcohol. Typically, this would be done in the presence of acid. Now, I'll be honest with you, this is very complicated because of the amino groups. The amino groups are certainly more basic than the carbonyl of the carboxylic acid, which needs to be protonated here. So you'd probably use a fancier way of coupling the alcohol and the carboxylic acid, but we're going to pretend like acid would be fine and acid catalyst would be fine. Of course, you probably can't be catalytic because we're going to protonate all the amines. So we're going to pretend that acid will be fine to couple the alcohol with the carboxylic acid. So there might need to be some workup or something at the end. We're just going to keep it simple right now. Okay, so this would represent our disubstituted benzene key intermediate. We need to make this. Now, there's the amino group here and the carboxylic acid. We know the amino group is made via the nitro group, and we can see that the two substituents have this para relationship. Well, the nitro group that the amino group comes from is a meta director. Carboxylic acids, these are electron withdrawing groups as well. These are certainly meta directors. Let's think about how we've installed the carboxylic acid group. There are two ways that we've done that in this lesson. First, would be the benzylic oxidation using potassium permanganate. And the second involves generating a Grignard reagent and adding it to carbon dioxide. Both the alkyl group and the bromine group would be orthopara-directors. The alkyl group has an advantage that it is big and will block the ortho position. So para would be the predominant product from nitration of that alkyl benzene. So let's go with that. Let's go with alkylation first. Meanwhile, bromine's small and you'll have ortho and para nitration of bromobenzene. So let's go with the alkylation. We've been using isopropyl chloride as we've set up for these benzylic oxidations, and that is because we know it's required that the benzylic carbon have at least one hydrogen, right, for the benzylic oxidation. But the Friedel-Crafts alkylation requires a stable carbocation. So secondary is a good compromise. Secondary is not as stable as tertiary, but it's more stable than primary. We haven't been proposing primary cations in Friedel-Crafts alkylations. So secondary is stable enough, but will still have this one hydrogen that is required for the benzylic oxidation. Let's not get too excited and do that benzylic oxidation right now because we need to exploit the fact that this is a bulky electron donating group. So although it is an ortho-para director, really the ortho position is going to be blocked since it's so bulky. So let's exploit the para-directing prowess of that alkyl group before we oxidize it to the meta-directing carboxylic acid. From the alkyl benzene, we will perform the benzylic oxidation now that we've used the directing abilities of that alkyl group. Now that the benzylic carbon has been oxidized to the carboxylic acid, we can focus on reducing the nitro group to the amino group. We'll use iron in the presence of HCl, followed by a workup. Just because those are the conditions that we usually use to convert nitro to amino. But you're going to notice, well, but the carboxylic acid will get deprotonated by the sodium hydroxide. Like there's a lot of acid-base incompatibilities to be thinking about here. We're just going to note that that's going to be an issue. And the solutions to those incompatibilities are, beyond the scope of this class, but you'd work it out in the lab if you were trying to really make procaine. Okay, so then we have this key intermediate. We're going to treat it with the alcohol and acid, or probably use a fancier reaction that I'm not going to teach you to convert the carboxylic and alcohol into an ester and make procaine. All right, that was fun. A lot to think about there. Let's summarize nitration and reduction to anilines. Benzene is converted to nitrobenzene in an electrophilic aromatic substitution reaction with nitric acid and sulfuric acid. Nitrobenzene can be reduced to aminobenzene or aniline in the presence of a solid metal reductant such as iron or zinc metals, followed by neutralization. We will now compare and contrast these three benzene derivatives in terms of directing effects and relative rates of reaction in electrophilic aromatic substitution. Nitro is a very strong electron withdrawing group. So nitrobenzene is not very electron rich. Thus, it has slow rates of electrophilic aromatic substitution. And any additional electrophilic aromatic substitution reactions will be directed to the meta position. For example, if a bromination is conducted on nitrobenzene, the bromine and the nitro groups will have a meta relationship. And nitrobenzene will react slower than benzene in this reaction. The amino group in aniline, aka aminobenzene, is certainly a strong electron donating group. So we might predict the fastest rate of additional electrophilic aromatic substitution. But really, in real life, electrophilic aromatic substitution reactions of anilines, of aminobenzenes, they're really complicated because the amino group is such a strong electron donating group, because it's so Lewis basic. Like, let's imagine that aminobenzene was treated under bromination conditions. The amino group, being so Lewis basic, would actually coordinate to iron. However, this is pretty wild. This amino group is such a strong electron donating group that bromination will actually occur without a catalyst. And that's good because the catalysts are really just kind of mess it up by coordinating to the amine. So no catalyst is necessary, but there's a crazy product mixture because this can actually just keep reacting. It's so electron rich. So oftentimes we just avoid, we really avoid electrophilic aromatic substitution reactions with anilines, with aminobenzenes, because there are product mixtures. This can make the tribromo product as well. There are product mixtures. The amine interferes with the catalyst, like Friedel-Crafts alkylations can't do those because the amine will coordinate to the aluminum. And then let's imagine that we did nitration. I'm going to regret showing this to you, but let's say we subjected this to nitration conditions. We would actually observe after workup the meta product. And you might say, what? Well, what is going to happen if you treat aminobenzene with nitric acid and sulfuric acid? It's going to be protonated, right? So what we have happening is aminobenzene gets protonated by the nitric acid and the sulfuric acid mixture, generates this intermediate. And while the protonated amine, the ammonium, that's going to be a sigma electron withdrawing group. So that is going to direct meta. So what is the bottom line of this whole discussion? I would just avoid doing anything to aminobenzenes because it's a mess. I'm not sure how we're going to write this. Let's just write like avoid. The solution to that is this acid analyte. So the aminobenzene can be converted to acid analyte. And in a way, you're protecting the nitrogen here. So we can make amides from amines with acid chloride. And then we add pyridine to soak up the HCl that's going to be formed in the reaction. We're protecting the nitrogen as an amide because now this lone pair that was causing so many problems for aminobenzene, that lone pair is delocalized in this pi system here. So it's less of a donating group to the ring. So that makes it an electron donating group, and that the lone pair can still be donated to the ring, but much less so than the parent amino. So it is an ortho para director. There's going to be no funny business. And it will be faster than benzene in electrophilic aromatic substitution reactions. For example, if we took acid analyte and treated it with bromine in the presence of iron bromide, we would observe a single bromination at the para position. This is a pretty bulky group, and it blocks the ortho. We'll come back to this acid analyte as an intermediate in synthesis when we wrap up and do some practice problems at the end. All right, be sure you have this down. And then we're going to move on. Our goal for this final section is to propose a synthesis of methyl orange, which is an azo dye. This is the azo group, and this is orange, a very brightly colored water-soluble dye. We want to propose a synthesis of that from benzene. Now, obviously, it's going to involve two equivalents of benzene. So two aromatic molecules are going to be formed and then coupled together in this diazo coupling. So we'll come back to this because that azo bond is made from an aryl diazonium salt. We have mentioned aryl diazonium salts in the introduction to this lesson. So aniline can be converted to aryl diazonium salts. Now we know how to make aniline from nitrobenzenes. And then aryl diazonium salts can be converted into many, many things, many functional groups, including azo dyes. All right, so we have to get through all the rest of these functional groups, and then we can get to the azo dyes. Let's do that now, starting with how to make the diazonium salt. Although this seems like an incredibly odd transformation, this aryl diazonium salt and derivatives of aryl diazonium salt, so if there's some R group on aniline, okay,
These just are incredibly useful synthetic intermediates. And they can be formed by treatment of anilines
with sodium nitrite in the presence of HCl. Let's learn how this happens. Sodium nitrite will react with HCl similarly to how nitric acid reacted with sulfuric acid in the nitration reaction that we learned in the electrophilic aromatic substitution lesson. Aqueous hydrochloric acid produces hydronium immediately, so I'll be using hydronium as the acid here. Hydronium will protonate nitrate to generate nitrous acid. Nitrous acid can be protonated again. This part in particular reminds me of protonating nitric acid with sulfuric acid, making a good leaving group, water, which can be eliminated in a nucleophile elimination of sorts. Lone pair push, expel water, yielding the nitrosonium ion. A super electrophile, a high energy electrophile, has been generated. Now, in electrophilic aromatic substitution, the ring would add to the super electrophile, but there's an amino group on the ring, and the amino group is definitely more electron rich than the ring. As we discussed, how electrophilic aromatic substitution should be avoided with anilines because then the amino group is so electron rich, it reacts instead. So that happens here. A nucleophile addition to the nitrosonium ion generates an intermediate that looks somewhat acidic. It's a protonated amine, except you have this nitrosyl group on the amine, so it looks pretty acidic. Proton transfer reaction with water as a base generates a neutral intermediate. Well, now what? Yeah, that's a great question. Well, look at the product. This oxygen is not in the product, right? How do we think oxygen is going to leave? Yeah, it's going to leave as water. That would be my guess as well. And we can go ahead and put that in. So we'll just put in plus water here. So we think oxygen is going to leave as water. Great. So we better start protonating it. Just generated an equivalent of acid in the previous step. So the oxygen can be protonated, generating this intermediate. Now you might notice there's a lone pair adjacent to a pi bond. This is actually a conjugated pi system, a 3-atom conjugated pi system with 4 pi electrons. And it can be represented with resonance structures. An examination of those resonance structures suggests that this resonance structure with the positive charge on nitrogen is the major resonance structure, the most contributing, whereas the one that we initially drew was the minor resonance structure. So perhaps this elementary step is best described as a lone pair push, forming a double bond here. And then these electrons that we're showing in the pi bond, those are actually the ones accepting the proton, forming this bond. It's probably best to show our curved arrows directly to the major resonance structure, so we'll do that. This intermediate we have described by resonance structures has an acidic proton. The stress on that molecule certainly is the positive charge on nitrogen, which can be alleviated by deprotonating in a proton transfer step like this one. Quickly comparing to the structure of the product, we can see we're getting so close to having completed the curved arrow mechanism. One more proton transfer reaction, protonating the hydroxyl here, will yield water, which can be eliminated. One final lone pair push, one final nucleophile elimination step, and the diazonium salt is formed. Water, these electrons make a triple bond, and then this lone pair is still implied on the diazonium cation. That mechanism wasn't so bad, huh? So we've showed how the aryl diazonium salt is formed, and now let's think about how to use it. These are incredibly useful intermediates, and they react by a number of ways. As you might imagine, the N2 group is an excellent leaving group. It's nitrogen gas. It's one of the most stable molecules that we're aware of. So it's an excellent leaving group. Now, how it leaves really varies from reaction to reaction. Some of the mechanisms are known and some of them are unknown. We are not going to spend much time thinking about the mechanisms associated with these transformations. All of these reactions are overall substitution reactions occurring at the carbon that bears the diazonium group. I would like to briefly remind you of a conversation that we had during the nucleophilic aromatic substitution lesson. We talked about aryl halides, and we said they do not undergo SN2 reactions, right? In the NAS lecture, we were discussing the observation that some aryl halides, when treated with nucleophilic species, do seem to undergo substitutions, particularly when there is an electron withdrawing group, ortho or para, to that X group. However, that substitution does not occur by SN2 mechanism, as we discussed, because sigma star Cx is just in the middle of the ring, not happening. Nucleophile have to bust through all these carbon atoms. No. The LUMO, the orbital that accepts electrons, is unavailable for attack. So SN2, impossible. And we said SN1 seemed unlikely. And that was because an aryl cation would be formed. This carbon does not have any implied hydrogens on it. It has 2 electron domains. It should be, ideally is, an sp hybrid. Sp hybrids have linear geometry, but that is impossible without breaking the ring open. So aryl cations are really high energy. And I asked you a question, are there any leaving groups that can facilitate the formation of an aryl carbocation? And I said, oh, a really good one. We moved along. Well, there are few better leaving groups than nitrogen gas. I mean, think about it. If this bond breaks, alleviate the positive charge on much more electronegative nitrogen. Now there is this high energy cation, that's not great, but nitrogen is a gas in addition to being a really stable molecule, so it evolves. So this reaction is irreversible. So this is a great leaving group, and in fact, probably one of the only ones that can facilitate formation of this high energy aryl carbocation. Fun. So indeed, 2 of these reactions are known to proceed via SN1 mechanisms. That's the generation of phenol by treating the diazonium salt with water, as well as the treatment of the aryl diazonium salt with potassium iodide to generate iodobenzene. Both of these reactions are really useful. In the case of phenol, there doesn't have to be an electron withdrawing group on the ring like there has to be a nucleophilic aromatic substitution, so that's nice. The substrate scope, so what I mean is the variety of different substituents that can be on this ring is much more variable, which is good for aryl diazonium salts compared to nucleophilic aromatic substitution that specifically requires an electron withdrawing group that is ortho or para to the leaving group. So that means that all the phenols that one can make by a nucleophilic aromatic substitution, they're all going to have an electron withdrawing group, either ortho or para to that phenol. So this is an alternative to that. You don't have to have those electron withdrawing groups. In the case of iodobenzene, we haven't even learned a way to make aryl iodides yet. So this is it. So you need to make an aryl iodide. Diazonium chemistry is the only way that you have as an organic chemistry 2 student. So those reactions are well known to go via SN1 mechanisms. These that I have circled in the dotted line here, they proceed via radical mechanisms by single electron chemistry. So treatment of the aryl diazonium salt with these copper salts does lead to overall substitutions by radical mechanisms, and these have a name. They're called the Sandmeyer reactions. You might say, well, I already know how to make chloro and bromobenzene. Yes, you do, but sometimes electrophilic aromatic substitution is not ideal, and we'll see some examples of that. So the Sandmeyer reactions are good alternatives to these molecules, and the only way that you know to make an aryl nitrile. Fluorobenzenes can also be generated from aryl diazonium salts. And then if you notice on here at the bottom, this is weird. We have a substitution for hydrogen. Well, this is actually a pretty useful reaction because sometimes you need to use a directing group or a blocking group to put other substituents on the ring. Like, so imagine there's a bunch of other substituents on this ring, but then you don't need this group anymore. You want to remove it. So convert it into the aryl diazonium salts and then treat with hypophosphorous acid to replace it with a hydrogen atom. And it's like it was never there. All right, let's look at some examples of using these incredibly useful reactions in synthesis. Aryl diazonium salts introduce a whole new set of strategies for the synthesis of aromatic compounds. This is a really good example. Here we have meta-dibromobenzene. Thinking of a synthesis for this compound is challenging because bromines are ortho-para-directors, but they have a meta relationship. So they did not direct each other in an electrophilic aromatic substitution. So how can this product be made? We need an alternative, right? Here's another example of a molecule that cannot be made with electrophilic aromatic substitution. Ortho-para-director, ortho-para-director, but they have a meta relationship. Let's start with this example. See if you can propose a synthesis, and you know this needs to come from the aryl diazonium salt. So start with that information and work backwards. That's a huge hint. Give it a shot. So we do believe that one of the bromine substituents was installed via a Sandmeyer reaction, treatment of an aryl diazonium salt with copper 1 bromide, and by a radical substitution, bromine replaces the nitrogen group. Great, the last step solved for. Now we need all of this part. We know, of course, that aryl diazonium salts are generated from nitrobenzenes via anilines. We know that this intermediate will need to be formed by probably by electrophilic aromatic substitution. That's fine because nitro is a meta-director in electrophilic aromatic substitution reactions. Bromine is an ortho-para-director in electrophilic aromatic substitution reactions. These two groups have a meta relationship. They have a 1-3 relationship. Thus, we will install nitro first since it directs as desired. So nitration of benzene with nitric acid in the presence of sulfuric acid generates nitrobenzene. Treatment of nitrobenzene with bromine and an equivalent of iron 3 bromide results in a brominated intermediate via electrophilic aromatic substitution. In order to generate the aryl diazonium salt, the nitro group must first be reduced to an aniline. This reduction is accomplished by treatment with iron or zinc metal in the presence of hydrochloric acid, followed by an aqueous basic workup to deprotonate and generate the amine. Finally, the amine is converted to the aryl diazonium salt by treatment with sodium nitrite in the presence of hydrochloric acid. What was the hint that we needed to use the aryl diazonium salt in the synthesis? Yes, the hint was the meta relationship between two ortho-para directing groups. Keeping what we've learned in mind, let's try again. Now, this question is arguably a bit harder because this T-butyl group is present in the starting material, and it's an ortho-para director. So in order to install bromine, in this position, which is not ortho or para to the T-butyl group. It's meta to the T-butyl group that exists in the starting material. We will need a different strategy. That strategy is to put an even stronger ortho-para director, para, to the T-butyl group. And then now if this group is a stronger electron donating group, it might direct electrophilic aromatic substitution in exactly the position that the bromine is observed in the product. So give it a minute, think about what we've discussed today and what this mystery group might be. All right, the mystery group is the amide. So there's this acid analyte group that we discussed quite a few slides ago. Here it is. So given this intermediate as a hint, propose a complete synthesis of this disubstituted benzene from T-butylbenzene. Well, we know the acid analyte comes from the amine, where this bond was formed by treating the aryl amine with acetyl chloride and pyridine, which are simply the conditions necessary to generate amides that we have learned previously. We know how to make aryl amines from nitroarenes by reducing the nitro group with iron metal or zinc metal in the presence of hydrochloric acid. The nitro group finally can be installed in an electrophilic aromatic substitution reaction using nitric acid and sulfuric acid. Now with this electron donating group, that is bulky and does usually direct primarily to the para position because it's big and the ortho positions are somewhat blocked. However, the para position has an alkyl group on it, so that means that the ortho positions are the only possibilities for electrophilic aromatic substitution. And that means, it might take a little bit longer for the reaction to take place. It might occur at a slower rate because the ortho positions are somewhat sterically hindered. However, bromination will occur ortho to acid analyte, generating this intermediate. Now this entire group should be removed and replaced with hydrogen. We can do that via the aryl diazonium salt. It served its purpose, right? It directed to the bromine to the ortho position in this electrophilic aromatic substitution reaction. And now it's time to remove it, replace it with hydrogen. All right, to do that, we must first remove the acetyl group. We must cleave this bond. We will do that with hydrochloric acid, followed by sodium hydroxide neutralization. This hydrolysis step converts the amide into a carboxylic acid and an amine. The neutralization is necessary because under acidic conditions, the amine will be protonated. So this step just deprotonates it to make the neutral compound. Then, of course, the carboxylic acid, in this case, we don't care about it. I just put it up here so you could remember the acyl transfer chemistry from the last unit. Now, the ultimate goal is to still remove this amino group. It is removed from the diazonium salt. So to make the diazonium salt, we treat with sodium nitrate in the presence of hydrochloric acid. The last step is accomplished by this reaction. Treatment with hypophosphorus acid replaces the nitrogen, the N2, with a hydrogen. We did it! This group is removed and replaced with hydrogen. It served its purpose. So as we can see, synthesis of aromatic compounds can get a bit complicated, but we can do it by just thinking critically about the reactivity of these different substituents. There's just one more reaction of aryl diazonium salts that we must learn, and that is the azo coupling to generate these dyes. Let's give it a shot now. Aryl diazonium salts can be used to make synthetic dyes, such as this one, which is called methyl red. An electron-rich arene, which will react as a nucleophile, interacts with an aryl diazonium salt, which will act as an electrophile at nitrogen, making this bond and forming this diazo functional group. And this is an electrophilic aromatic substitution reaction, as it turns out. Lone pair push, over, attack. We could draw resonance structures of this starting material to show that the para carbon is electron rich. So are the orthocarbons, but the orthocarbons are blocked a bit by the methyl groups. Additionally, we can see the product, and the product is para-substituted. So we will draw those curved arrows. All right, so we have the pi electrons on the ring attacking at the nitrogen. This pushes these electrons onto the other nitrogen, relieving that positive charge and generating an intermediate that looks like this. As in all electrophilic aromatic substitution reactions, a non-aromatic cationic intermediate is formed and can be described by resonance structures. I have, however, drawn the most stable one. An electrophile elimination step, which in this case is facilitated by the solvent water, deprotonating these electrons coming, forming this pi bond. These slide over to here. These slide over, relieve the positive charge on nitrogen, forms the final product. It's not so bad, right? It looks scary, the big molecules involved, but it's just an electrophilic aromatic substitution reaction. Electrophile addition, electrophile elimination. Given this key step, it's time for you to propose a synthesis of methyl orange from benzene. I introduced this problem way back when, over here. Yeah, so it's time to try this problem. Give it a shot. Perhaps it's easiest to think about this with retrosynthesis. I always like to use retrosynthesis. I think everything is easiest using retrosynthetic analysis. We might come up with some final diazo coupling that looks like this. Then we need to synthesize dimethyl and this sulfonic acid. Let's tackle the dimethyl first because I think that that's easier and more challenging all at the same time. The dimethyl will come from aniline, and we'll need to make these bonds. And most of us have probably forgotten how to make those bonds. We will do that via reductive amination. Since one carbon is desired to be added to the amine nitrogen in this reductive amination, we'll use a one carbon carbonyl compound, which is formaldehyde, and sodium cyanoborohydride. Recall that in this reaction, the iminium is formed, and then sodium cyanoborohydride reduces it. Okay, the formaldehyde will make the iminium ion with the amine. The iminium ion is reduced, hydride adds. Okay, and that's going to make one of the methyl groups, and the whole process repeats itself to make the other one. How to make aminobenzene from benzene? Well, we can handle that. First, the nitration reaction. Then the product of this reaction, nitrobenzene, is reduced with iron or solid zinc metal in the presence of hydrochloric acid, followed by a basic workup to yield the neutral aminobenzene product. So one of the partners for the diazo coupling has been synthesized from benzene. Now it's time to make the other. Well, taking a look, we definitely can see that this is an electron withdrawing group, the sulfonic acid. And that means it is a meta director. So it would direct whatever this comes from, which is nitro, to the meta position, which is not where that is. That is para to the sulfonic acid. Thus, the sulfonic acid is installed after some precursor to the diazo salt, whichever one has an electron donating group. So let's go down this road here. So to install the aryl diazonium salt functionality, we start with nitration. That generates nitro, which is an electron withdrawing group, so we're not where we need to be quite yet. That, if we try to do the sulfonation now, that will go meta, not para, which is where we want it to go. Aryl diazonium salts are made from the aminobenzenes, so we do need to reduce this nitro group. Reduction with iron metal in the presence of hydrochloric acid, followed by neutralization, does generate the aminobenzene. And now we're in business, right? There is an electron donating group on the ring, which is a para-orthopara director. However, as we discussed right here, these groups, aminobenzenes, should really be avoided in electrophilic aromatic substitution, particularly when you're considering what the proposed reaction would be of this particular intermediate. You need to install a sulfonic acid. That involves treatment with fuming sulfuric acid. Fuming sulfuric acid will, like I mentioned earlier, just protonate this, turn it into an NH3 plus, make an electron withdrawing group, and it'll direct meta. So that is just not going to work. And the way that we discussed to get around this is to convert it into the acid analyte. Now nitrogen is much, much less basic because of its donation, it's conjugated to the carbonyl. However, it is still an electron donating group. There is still some donation to the ring. It's still conjugated with the ring as well. So all the bad aspects of the nitrogen are going to be avoided. Now the acid analyte can be treated with fuming sulfuric acid to install the sulfonic acid. Because the acid analyte is so big, it does block the ortho position and favor the para position. Now that doesn't mean that substitution can never happen ortho. We saw in the previous question it occur ortho to this group. But when the para position is available, that position does react faster. All right, sulfonic acid installed. Now, aryl diazonium, this intermediate, is going to be made from the amine. To break this bond and remove the acyl group from the amine, so to break the amide bond, is most easily done in the presence of acid. So we will hydrolyze with aqueous acid, but that hydrolysis would actually generate the protonated amine, so NH3 plus. So to avoid that, we will treat with sodium hydroxide to neutralize the protonated amine. Just understanding that sodium hydroxide will certainly deprotonate the sulfonic acid, and that just cannot be avoided, and it really doesn't matter. Okay, cool. So we have a salt of that. And we are almost there. Now to generate the diazonium salt, we will treat with sodium nitrate in the presence of HCl. That will also reprotonate the sulfonate to make the sulfonic acid. It really doesn't matter to us. Nothing's really happening there. So the protonation state of the sulfonic acid is sort of boring. All right, now time for the diazo coupling. Diazo coupling occurs in aqueous hydrochloric acid. In acid, the sulfonic acid will be preserved, and actually we want the sulfonate, and that just actually has to do with the dye being water soluble. So no problem. We'll deprotonate this to make the sulfonate with sodium hydroxide. All right, we did it. We made methyl orange. Take a look through that sequence again and be sure that you understand, and let me know if you have any questions. All right, summarize what you've learned about azo couplings. I will help you out a little bit. An electron-rich arene will act as the nucleophile, and the diazonium salt is the electrophile. As we discussed, an electrophilic aromatic substitution reaction occurs where this is the electrophile to form the diazo dye. So to summarize, at the outset of aromatic chemistry, I promised that you would love it because it follows rules. I want you to think about how you feel about aromatic chemistry and about the rules that it follows. So write down your answers to these questions. We have achieved the learning goals today. We can predict the products of common reactions of aromatic molecules. We already know the 6 reactions of electrophilic aromatic substitution. Just to remind you, those were these 6. We've also learned nucleophilic aromatic substitution reactions. Don't forget those reactions. And then finally today, in this lesson, we learned one seems random, so it's a reaction of the benzoic carbon actually, this oxidation of the benzoic position to make benzoic acids. Then we learned the sequence that turned out to be very useful, that nitrobenzenes can be converted to anilines, anilines can be converted to aryl diazonium salts, and then aryl diazonium salts can be converted to all these other functional groups. Then we practice using these in synthesis. And I would say the trickiest ones were the hypophosphorus acid reduction, because that is hard to see in the end because there's just a hydrogen there. But we did that when we used, this group as a blocking group or directing group. And then when to employ or when to use the nitro versus the amino never versus acid analyte. We saw some tricky synthesis problems. But as always, you will get this with practice. So it is time to practice. You have this problem, this problem, this one. Looks pretty similar, but a bit different. This one and this one. This is mechanisms though. So practice and let me know if you have any questions.